So this is going to be a relatively simpler chapter. Hope you people also had a good test on Sunday. So we have a second lecture this week. So maybe in that lecture, we will discuss any doubts and questions from the test also, in addition to other things. So let's look at quick recap of what we have learned so far in hydrostatics. What we've seen is that for an ideal fluid at equilibrium in an inertial frame, vertical pressure gradient is minus rho g. Whereas horizontal pressure gradient is 0. Okay, and therefore we have seen that if a point inside a fluid is at a depth of h with respect to an open surface, the absolute pressure at a point at depth h with respect to an open surface, so that absolute pressure is atmospheric pressure plus rho gh, and the hydrostatic pressure, or what we call the gauge pressure, is equal to rho gh. And based on this, we had done a couple of examples of calculation of force on a surface because of hydrostatic pressure, etc. So these kind of things we have seen. Okay. Then we also saw Pascal's law that any change in pressure is uniformly transmitted to all other points inside a fluid. So let's start with a couple of examples based on this. We'll start with a very interesting problem called the hydrostatic paradox problem. It's just called a paradox. Actually, it is a very easily explained situation, so it is not really a paradox. So anyhow, let's consider that we have 3 containers, which I'll draw in just a moment. So we have 3 containers like this. One is cylindrical, and the other are conical cylinders or conical vessels, you can say. So these are 3 containers, all having the same base area A. Container 1, 2, and 3, they have the same base area. Okay. And they are open containers filled with fluid up to the same level. So this one is filled up to here. This is filled up to here. So same fluid filled up to the same level. So containers, or you can say open containers 1, 2, and 3 of same base area filled with the same ideal fluid up to a common height h. Okay. Now, if weights of fluid in each are given by the relation W1, W2, and W3, and normal contact force of the fluid with the bottom surface, they are N1, N2, and N3. Then which of these are correct?
क्या बात करे यशमित, बोलो।
कुछ भी बात कर।
अबे तू पहले पकोड़े खाना सीख जा, उसके बाद बात करते।
अबे रिकॉर्डिंग तो बंद करो यार।
अबे तू ही होस्ट है साले, बंद नहीं
हाँ
कर
वही
सकता।
हो, तू ही होस्ट है, तू क्या बक रहा है बे?
बंद कर
अभी
फिर
जो
ये
स्टार्ट
स्पीकर
का
पे
रिकॉर्ड हुआ
रखो।
उसका क्या करूं? अबे फिर कुछ गलत ना
अबे
हो
देख
जाए,
के
मेरे को
बात
नहीं
कर तू।
पता।
सर ने कुछ मैसेज डाला
बंद
क्या?
करना रिकॉर्डिंग।
सर ने बस डाला कि पावर आउटेज उनके एंड से वो ट्राई करेंगे जल्दी जल्दी खत्म हो, बट
हाँ तो
नहीं हो रहा
रिकॉर्डिंग
अभी।
बंद करना है, तो रिकॉर्डिंग बंद करना।
Zoom recording, yeah. So understood the problem now. So we have three containers which have the same base area, open containers, but they are shaped in this way. One is a cylinder, the other two are conical vessels. One is tapering and one is broadening as you go up like this. Okay. Same base area, and they are filled with the same ideal fluid up to the same height. Okay. So now as a result of this, what happens is that if the weight of the fluid in each of the containers is W1, W2, and W3, whereas the normal contact force that the fluid is applying on the base of the container, okay, or the base of the container is applying on the fluid, whatever. So the contact force between the base and the fluid, that is N1, N2, and N3. Then we have to say which of these options are correct. Okay, so option A is, let's say, W3 is greater than W2 is greater than W1. Okay, then option B is W3 is greater than W1 is greater than W2. Then option C is that N3 is greater than N1 is greater than N2. And option D is N3 is equal to N1 equal to N2. So there's a more than one option question correct, let's say, more than one correct option. So which are the correct options? Just think about the question carefully once and send me the answers. Or so when you visualize the weight of liquid in the container as the volume into density into G, right? You can understand that they are having different volumes of liquid. Okay. So obviously the weights will be different. But when you talk about the contact force at the bottom, it should be pressure into area because it will have a uniform pressure. I'm just waiting for your answers. Which are the correct options? Yes, that's correct, Dhruv. Okay. So Parth and Samarth, unfortunately, your answers are not correct. Okay. So to think along the lines of what I'm saying, okay, the weight of liquid in a container, it should be equal to what? mg. So m should be equal to the density of fluid into volume of fluid into G. V is the volume of fluid. So by this logic, you can definitely see what is happening. Volume of fluid is maximum in the third container, minimum in the second container. So weight in the third should be maximum and weight in the second should be minimum. So this option definitely should be correct. But when we talk about normal contact force, on the bottom surface, then you should understand that this is experiencing a normal force which is equal to the pressure into area, and that to the hydrostatic pressure, because we are considering what pressure, what force the liquid is applying. Okay, not the liquid plus the atmospheric pressure, but the liquid pressure, how much force it is applying. So the presence of the liquid is creating a additional force due to the additional hydrostatic pressure. So that is equal to how much? That is equal to rho g h into area. Now h is the same for all three containers, that we already said. The level of liquid is the same in all three. So the vertical height of the liquid column is the same. So what does this seem to suggest? This seems to suggest that normal reaction should be same in all three. Okay, so ultimately that is the correct answer. So option D is correct and option B is correct. Okay, yes, Aditya and Rakshit, you also got it correct. But then do you see some kind of contradiction happening over here? If normal reactions are equal but weights are different, then how can we justify from Newton's second law that net force should be zero? Okay, the explanation I've given here is correct. Okay, but then how can we justify this result in terms of Newton's second law? Of course, normal reaction is a vector only, but Shikhar, how option B is correct? You can see the volume of liquid in which container is maximum. You can see in third container volume is maximum, no? And in second container the volume is minimum. If you just look at the shape of the containers, you will realize this, no? They're all having the same base area. Okay. But the third one is like this. The first one is like this. And the second one is like this. So compare the volume of liquid in the containers. So it's easy to understand that volume of the third container's liquid is maximum. Is it clear? Okay. So how can we justify that normal reactions are different, but rather normal reactions are same, but the weights are different? Okay. So the justification of that comes from the proper free body diagram where you consider all the forces. So for example, if you consider the liquid in the first container, just the liquid's free body diagram. What is the net force on the liquid because of the side walls? The force that due to pressure from the side walls, they are like this now. So they're
Yes,
cancelling each other.
Yes, sir, they are increasing
Yeah. So
along
this
with height.
normal reaction should be equal to the weight in the first case. So N1 should be equal to W1. But look at the liquid in the second case now. I think the second case was like this. Yes. Okay. So here it's a conical vessel. So the side walls will be applying force like this. So there will be some net force due to the side walls. Okay, because the liquid is applying pressure, force due to pressure in the opposite direction. No? So this is that reaction force that the side walls are applying. So you can say that,
Components हो गया ना sir, perpendicular.
yes, हाँ, components लेके ऐसा हो जाएगा. So this F is the net force due to the walls of the container. So that will be in the downward direction, whereas the normal reaction that the floor is applying is still in the upward direction, and weight is like this. So in this case, you can see that the weight, okay, will be equal to this normal reaction minus F. So in this case, you can see that the weight is actually equal to less than the normal reaction. Okay, whereas here the weight was equal to the normal reaction. And in the third case, you can see the opposite is happening. Third case, the fluid body being in contact with the surface, the side walls are applying force in this sort of direction. So इनका जो vector sum है, horizontal components cancel होंगे, but vertical components together will create some force in the upward direction, let's say F prime. So that is the net force that the walls are applying, whereas the floor is applying force like this and the weight is like this. So in this case, the weight is more than the normal reaction at the floor, because the walls are also helping in supporting that weight because they are applying a net force upwards. Okay. So here F prime is the net force due to side walls. So ultimately, there's no paradox here because the problem is very easily explained by the normal laws of physics itself. Okay. So the three normal reactions are same, but the weights are different. One weight is more than the normal reaction, one weight is less, and one weight is equal to the normal reaction. So we have the weights in that kind of order, that W3 is greater than W1 is greater than W2. But N1 is equal to N2 is equal to N3. Okay. So there are a couple of interesting questions on H.C. Verma which are based on numerical calculation based on this concept. Okay, so we'll be trying them out and pretty easy they'll be to work out. Okay, now next let's look at an example with an application of the Pascal's law kind of principle. So next, let's say we have this kind of a tube which we have bent into a U kind of a shape. So initially what we have done is we have kept water filled up to some height like this. So these are open surfaces like this. So this is water which has a density of 1 gram per cc and it's filled up to a height h0, let's say. So obviously this height will be same on this side also. So this h0 is, let us say, 80 centimeters. Now what we do is we pour water from one side, okay, and as a result of that, sorry, we pour not water but some immiscible fluid like kerosene or something. So let's say we pour some kerosene oil from one side. That changes the level of water on either side. Okay. So let's say on pouring kerosene on the left hand side, there is kerosene being an immiscible fluid. So there will be a layer of kerosene which is floating on top of the water. Okay. So that column of kerosene which is floating on top of water, let us say that that height of the kerosene column is observed to be some x. Okay. So if we pour kerosene from this side, what we'll observe is that this side the level of water will come down compared to H0. Okay. And this side the level of water will have gone up compared to H0. Because we have poured some oil over here. So an immiscible oil like kerosene oil is poured from this side. And as a result of that, the level of water changes. Kerosene oil, which has a density of, let's say, 0.6 gram per cc, okay, is poured into the left column, okay, such that x is, let us say, 40 centimeters. So we want to find H1 and H2. The new level of water on either side, we want to find that. Okay. Just try this out. There's a pretty easy application of Pascal's law. By pouring kerosene at one side, okay, we are changing the hydrostatic pressure of water in that column. So that change in pressure translates uniformly or transmits uniformly to all other points within the water column. So that is the concept that we'll be applying over here.
Sir, can you show the above part for a minute?
The other problem, the hydrostatic paradox one?
Yes, sir. I had some network problem.
Okay. So this is the explanation for that.
Okay, sir. Yes, sir. Got it.
Okay.
Sir, 1 second, can you scroll down?
Okay.
Yes, sir, done.
Okay. Durgesh, H naught was 80. I think the way you've done the calculation, sorry, Aditya, you might have taken H naught as something else. Have you taken H naught as 40 by mistake instead of 80?
So let me try. Sorry.
I think your approach is correct. You've just taken the wrong value of H naught. H naught is 80 centimeters. Okay. On this side, H naught is 80 centimeters. Now we have to find H1 and H2. Yeah, Parth, I think your answer is correct. Okay. If my calculation is all right, H1 should come out to be 68 centimeters and H2 should come out to be 92 centimeters. Okay, so let's understand how this is working out. So if we take this point here as, let's say, A and this point here as B, then pressure of A and B should be equal because they are 2 points at the same horizontal level in the same fluid. Okay. So pressure at the point A should be equal to pressure at the point B. Now, we cannot directly write the pressure at the point A because there is 2 different fluids above it. But if we introduce this other point C, so we can see that the pressure at the point A will be atmospheric pressure, or let's say it is equal to pressure at C plus density of water into G into H1. Whereas on the other side, pressure at the point B is equal to pressure at the open surface, that is atmospheric pressure, plus density of water into G into H2. Now further, pressure at the point C, that will become how much? The pressure at an open surface plus, now we can consider the point C just between the water and, I mean, just at the surface of contact. So above it, we have the kerosene layer. So density of kerosene into G into X. That is the pressure at the point C plus this. So that's the pressure at the point A. And that should be equal to the pressure at the point B, which is. So from this equation, you can see that we get a relationship between these, that density of kerosene into X is equal to density of water into H2 minus H1. Or the difference in the two levels is going to be relative density of kerosene into X. So now I'll just substitute this numerically. So I have H2 minus H1 should be equal to 0.6 into, what was it now, 40. So 24 centimeters is the difference. So let's say this is our equation 1, and this is coming from the concept of, you can say, hydrostatic pressure concept or application of Pascal's law or whatever. Now the other thing is that total volume of water is conserved because we are assuming none of the water is leaking out of the container. So we also have conservation of volume. Okay, so volume of water, that is in the first diagram 2h0 plus whatever this length is into some area of cross section. In the second diagram, it is equal to h1 plus L plus h2 into the same area of cross section. So it is equal to, so h1 plus h2 should be equal to 2h0. This is a very intuitive equation that whatever the level will go down on this side with, it has to come up by the same on the other side. So h1 plus h2 should be equal to 2h0, which is equal to 160 centimeters. Now all we have to do is solve these two equations, equation 1 and 2, and we'll get these values, which I have written down. Okay, so hope this is clear to all of you.
Sir, please wait 2 minutes.
Yeah, Shikhar, we cannot do directly the second step over there, na, because we can write that pressure difference only in terms of a single liquid's density. Na. We cannot directly add the two columns of liquid density. Okay, that pressure gradient del P by del X is equal to rho G. That applies to, or minus rho G applies to a single liquid at a time. That's why we have to consider the split column like that. Okay. For example, you will also understand one thing, that if you take a point inside kerosene like this over here and see another point inside water on the other side, the pressures will not be equal. Okay, because they need not be equal also, because they're not in the same liquid. So there's nothing that says that in two different liquids which are static, the pressure at same horizontal level should be same. Okay, so that whole concept of horizontal pressure gradient is 0 and vertical pressure gradient is minus rho G. That applies to a single body of liquid like that. So okay, now let's come to one of the most important applications of concept of pressure gradient, and that is the statement of Archimedes principle. Okay. One of the most famous eureka moments in physics that you would have heard legends about. So Archimedes principle, the statement of it is that when a body is submerged in fluid, okay, whether it is completely submerged or partially submerged, it always tends to experience an upthrust or an upward force. And that upthrust, or what we call buoyant force, equals to the weight of fluid which is displaced. Okay. So the statement is, any body submerged, okay, whether it is partially submerged or fully submerged, in a fluid, experiences an upthrust, which can also be called buoyant force. This property of the fluid to apply upthrust is called buoyancy. Okay. Which is an upwards force equal to, now this is the most important thing, equal to the weight of fluid displaced by the body. So this statement literally means something like this, that if we consider in a fluid anything that might be partially submerged, okay, or anything that might be completely submerged. So we can have something which is partially submerged because it is suspended like this inside the fluid, or something that is fully submerged because it is suspended completely inside the fluid. But in both cases, the fluid will be applying some kind of force on it, which will be a vertically upward force called the buoyancy or the buoyant force. And that buoyancy will be equal to, or buoyant force will be equal to, the weight of fluid displaced.
Sir, can you explain this point again?
Yeah, it's just written over here. There's nothing further to explain. It's in the definition. The buoyant force is equal to weight of fluid displaced. Okay? So buoyant force equals to, now what is the weight of fluid displaced? It is the density of the fluid multiplied by the volume of the
Into it,
submerged
yeah.
part into G. So here, this term V sub, it is equal to the volume of the submerged portion of the body. And of course, B over here is the buoyant force, or alternatively, we can call it the upthrust also. So this is just a property of any fluid or any body inside a fluid, which Archimedes observed and gave the definition of. So there's nothing further to explain in this. This is the definition in itself. Of course, this definition can be derived. This formula can be derived using hydrostatic pressure. So that we'll look at next. But first, just note down the definition. So upthrust or buoyant force experienced by any body which is submerged inside a fluid, whether it is partially submerged or completely submerged, that amount of upthrust equals to the weight of fluid displaced by the body.
Sir, is this applicable for objects that float?
Sorry, is this, yeah, it is applicable for objects that float also. So in the case of floating objects, what happens is that the buoyant force is enough to balance the weight of the object. But here, for example, I have considered not a floating object, but an object which is suspended underwater, because it might be a heavier object like a concrete block or a metallic object. So if I cut the thread, it will tend to sink. But I've kept it either partially submerged or completely submerged in the first or second diagram by suspending it using a thread inside water. But what we will see next is that the tension in the thread will not be equal to the weight. It will be less than the weight because the fluid is also applying some kind of force on it, which is called the buoyant force. Okay, so now let's understand how this exactly happens. And before we do that, let's also understand the free body diagram of the object in each case. So in this case, the object is partially submerged. So the fluid will still apply some force on it, and that is equal to buoyant force. And this is the tension. And let's say this buoyant force is B1 because it's partially submerged, and its own weight is mg. So here, tension in the thread plus buoyant force will be equal to the weight of the object. So you can see that the tension will be less than the weight, but the buoyant force will be equal to the density of fluid into, let's say, V submerged into G, where V submerged is the volume of the portion of the body submerged in the fluid. It is not the full volume. So that is what the free body diagram will look like in this case. Whereas in the second case, where it is completely submerged, let's say the buoyant force is B2 and the tension in the thread is T2. In the second case, the tension will be different because the buoyant force is different. And why the buoyant force is going to be different in this case? Because now the submerged part's volume is how much? It is the complete volume. So in this case, it is density of fluid into, we can say, V into G, where V is the total volume of the body because it is completely submerged. So this is what happens when it is the fully submerged case. Okay. Whereas this is what happens when it is the partially submerged case. Part of it is submerged. So that is the difference between these two examples that I've shown of partially submerged objects suspended inside a fluid and fully submerged objects suspended inside. And of course, like you pointed out, that one of you pointed out that an object can also float because of buoyant force, like a wooden block or an iceberg floats in water. Okay. So that happens because the buoyant force is so large. I mean, the buoyant force is enough compared to the weight of the body to actually make it float without any third force present. Now the whole question is, why should it exactly be equal to this formula? That is density of fluid into volume of submerged part into G. Why should it exactly be that? So the proof of that actually comes from the concept of hydrostatic pressure gradient. Of course, when Archimedes had come up with this definition, he did not think in terms of pressure gradient. He just solved this by a logical kind of observation of the situation. Okay. So let's understand how exactly this works. So now consider like a cubicle shaped object. Okay, which has been kept submerged under water. So this is a cubical solid body, dimension L by L by L, okay, which is placed under water or under inside some fluid. So how it is exactly placed over there is just like the previous example. Suppose we have kept this suspended by means of a thread or something, such that it's completely dipped under the fluid level, like this. Okay. So what is going to happen is, now let us say the depth of this surface is h1 and the depth of this second surface is h2 from the open surface of liquid. Okay. So this level difference is L. Okay. So when you consider the force acting on each of these surfaces because of pressure, what you'll understand is that these forces cancel each other. The forces on the side walls, they cancel each other. But the forces that are experienced by this surface from above, let's say F1, and this surface from below, they will not cancel each other. Okay. So F prime is the force on each side wall of the cube due to hydrostatic pressure. So in pairs, the four F primes, they cancel each other. Okay. But if you consider F1, it is the downward force on the upper surface of the cube due to pressure, hydrostatic pressure. And similarly, F2 is the upward force acting on the lower surface due to this. So F2 you can see is greater than F1 because pressure increases with depth. Okay. So the net force that the liquid is applying because of this pressure that is applying on each of the 6 sides of the cube, that net force will be in which direction? It will be in the vertically upward direction because the horizontal ones all cancel in pairs. So that net force is only what we call buoyancy. Okay. So if we look at the side view diagram only, we can see that two of these horizontal forces, F prime and F prime, they are cancelling each other. Okay, the other two are also cancelling each other, but these two forces are not cancelling each other. So the net force that the liquid is applying is F2 minus F1. Okay, and that is equal to the what we call the upthrust or buoyant force. So the net force or upthrust applied by the fluid on the submerged body that is equal to F2 minus F1. Now that will be equal to fluid pressure at that depth into the area minus fluid pressure at the depth of the upper surface into the same area. So as you can see, it is the density of the fluid into G into H2 minus H1 into the common area, which is L square. And H2 minus H1 is also L. So it is rho G L cube. You can see that it is equal to the weight of fluid displaced. Okay. Here rho is the density of the fluid. Okay. So it is because now we have shown this for a cubical shape, but any shaped container or any shaped body inside a fluid, its lower surface will experience more pressure than its upper surface. And that pressure difference, okay, into the area, that will always result in the net upward force, which will be equal to this kind of relation. It will be equal to the density of the fluid into the volume submerged, which in this case is L cube into G. This is rho, this is L cube into G. Now, just like I've proved it here for a partially submerged object, we can use the same kind of logic and show it also for a, sorry, I have proved it here for a fully submerged object. Now we can use the similar kind of free body diagram and pressure gradient method to prove it for a partially submerged object also.
सर
So-
उसमें खाली h minus h का वैल्यू थोड़ा डिफरेंट होता है.
हाँ, only instead of H2 minus H1 being equal to L, one surface will be outside, so it will be at atmospheric pressure, and the other surface below will be at some, you know, different pressure. But that pressure difference will depend on the portion of the part which is submerged or portion of the body which is submerged. So ultimately we'll get the same thing, that is density of the fluid into volume of submerged part into G. Yeah. So this is showing you why the liquid applies an upward force on any body which is submerged, because the lower surface of the body experiences more pressure compared to the upper surface. So the upward force with which the liquid is pushing the lower surface, that will always exceed the downward force with which it's pushing the upper surface. F2 will always be greater than F1. And the difference of F2 and F1 will always be the weight of that much part of liquid, which was supposed to be present over there if the body had not been there. So that is nothing but the equivalent weight of liquid which has been displaced by the body. Yeah, so people unfortunately some major precipitation at my end, so network issues. Just share the screen again. So unfortunately, my internet connection is having some like major data issues, data transfer issues because of probably the very heavy rain. So anyway, let's continue as much as we can, at least complete this portion. I will send you the recording and the lecture notes as soon as possible. So hope you understood this derivation first of all, this one.
Yes, sir.
Okay. Now, similarly, you can see that if you have a partially submerged object, you can easily similarly prove it. Okay. Yeah, Sujal, I understand. Today, everybody must be having network issues from morning because of the cyclonic weather.
Yes, sir.
But then at the same time, it's good relief to have some rain. So if we have something which is partially submerged, okay, let's say the portion which is submerged, this is X. Okay. So what will happen is that this surface will experience a force of atmospheric pressure into whatever area, whereas this will experience a force of atmospheric pressure plus rho gx into the same area. And again, the side forces will cancel out. So the net upthrust or buoyant force on this object will again be, you can see this pressure difference into that area. So again, it is equal to density of the fluid into volume of submerged part into G. Okay, so this becomes a universal equation. Whether an object is partially submerged or fully submerged, this becomes the general equation. Okay, so let's see an interesting question based on this. Okay, so what happens is we have a metallic object, okay, of volume V in cubic centimeters, okay, and of density of metal is, let us say, so the density of the metal, let's say, is 12 gram per cc. Okay, now it weighs, so this object, when we weigh it in air, it weighs, let us say, 56 grams in air. Okay, now when submerged in water, completely, that is, okay, it weighs, let's say, it weighs 51 grams. Okay, density of water we know is 1 gram per cc. So assuming there are some cavities in the object, you have to find the volume of the object, okay, and the actual volume of metal in the object. because it has some cavities inside. So what we'll assume here is that the cavities are inside the object. So, water cannot get inside the cavities. So from outside you're seeing it, it looks like a solid metallic object, but you know that inside there are some cavities. Now, how you know that? This data will suggest that. Okay, when you correlate this data with the concept of buoyancy, it will correlate that 56 gram it's weighing in air, and it's made of material which is of density 12 grams, but underwater it is weighing only 51 grams. So that data will suggest that it's not completely solid. It has some holes inside, and the holes are inside. So water cannot get into those holes when you submerged it. Okay, so using these two pieces of data, that in air it's weighing 56 grams, whereas underwater it is weighing 51 grams, can we actually estimate that what is the volume of the cavities in it, or what is the actual volume of metal? So the total volume of the object minus the actual volume of metal will be the volume of cavities. So this is, for example, a method that, this is similar to a method that is used by goldsmiths and all to estimate the purity of ornaments, etc. This is a crude method. Nowadays nobody uses this method. Okay, but this was a method that was used at once upon a time to understand whether there was any impurity mixed along with the precious metal in ornaments, etc. Just try out this question. Exactly, Jagannath, that's correct. The modern day techniques for these okay, so let's understand how we can solve this from this particular data that is given to us. So when we weigh the object in air, okay, so let's say we are using a spring balance or something like that. Okay. So the tension in the spring balance at that point of time is equal to its true weight, okay, which according to the information should be equal to 56 grams multiplied by acceleration due to gravity. So the mass, which will be equal to the density of metal into the actual volume of metal, that is equal to 56 grams. Okay. So in other words, the volume of metal present is 56 divided by 12 in cubic centimeters. So this is not necessarily the volume of the object or the outer volume, you can say. This is the volume of metal present. So this is, you can also say it is equal to the volume minus the volume of cavities. Okay, so next up, if you look at what's happening when we repeat this whole weighing of the object business, but underwater. So obviously, what we're measuring as the weight is the tension in the spring or in the spring balance or whatever. That is now changed because of the additional force of buoyancy which is acting on it, and is completely submerged in water, remember. So this new tension is mg minus buoyant force. Now this tension is nothing but the weight in water. Okay. So that is equal to 51 grams. So mg minus buoyant force is 51 grams into g. Okay. Now what will be the buoyant force in this case? It will be equal to the density of water into the total volume of the object into g. Okay. So density of metal into volume of metal into g minus density of water into volume of of the whole object into g. This is equal to 51 grams into g. So this is what our second equation is giving us. Whereas our first equation here, let's say this one, was giving us this. So when we substitute this, we can first of all understand that 56 minus density of water into V is equal to 51. So that means so the volume of the object itself is 5 grams divided by density of water, which is 1 gram per cc. So it is 5 cc. Okay. So the total volume of the object that is equal to 5 centimeter cube. Okay. Whereas the volume of metal present, that is only 56 divided by 12, which you can see is a little bit less than 5. That is about 4.67 cubic centimeters. So the cavity volume is the difference, which is about 1/3 of a cubic centimeter. Okay, next principle based on concept of buoyancy, let's pick up is,
So could you please go back one line?
scroll back. Okay. You can see you have to just compare these two free body diagrams. Okay, one in the case where there are the three forces including buoyancy acting, and the other in the case where just the true weight is being balanced by the spring force or whatever force the weighing balance is applying.
Done, sir. Thank you.
Okay. Next, let's understand the physics of a floating object and how we can apply Archimedes principle. So the idea is that for an object to be able to float, there must be sufficient buoyant force or upthrust to be able to balance the weight of the object, right? So typically a floating object floats in such a way that it is partially submerged. Like consider a wooden log which is floating. So the net force on it must be zero, which means that its weight is balanced by the buoyant force. So the equilibrium condition, or what we can call the floating condition, is that the buoyant force balances the weight of the object. So density of fluid multiplied by volume of the submerged part into G must be equal to the weight. Now further we can see that if the object happens to be a solid object, like a solid log of wood made of isotropic material, so its own density is uniform. In that case, we can write the mass as the density into the total volume. So if the object floating is a solid and isotropic body, so isotropic means it has uniform density. So let's say that density is rho. Then we can write the mass of the object as density into V, where V is the total volume. So then we get that other secondary equation that the fraction of volume submerged will be nothing but the relative density. So this equation will imply that density of fluid multiplied by the submerged part's volume should be equal to the density of the material multiplied by the complete volume into G. So fraction of volume submerged for the floating object becomes the density of that material with respect to the density of the fluid. But remember, this is a special case of the above equation, the floating equation or the floating condition, when the material is of this type or when the body is made of isotropic material and it is solid. Only then we can replace the mass with something so simple that it's a uniform density into the total volume. So this equation above here, this is universal for any floating object. Okay, it might be a log of wood with patches of metal inside it, or with non-uniform density, or with cavities inside it, anything will work here. But this equation that we've written below, this is subject to the condition that the object is made of isotropic material and it's solid.
So can you please explain the last part again?
So last part means, what we are doing is we are saying that the object, if it is solid and made of uniform density material, then the mass of the object is what? Density into volume, total volume.
Yes, sir.
So we are just substituting that in the above equation. Mg ka value kitna ho jayega? M, which is density into volume into G. Whereas on the other side, buoyant force, it remains the same. So you just see the ratio of submerged volume to total volume comes out to be the ratio of the densities.
Yes, sir.
Yeah, Shikhar, to answer your question, can buoyant force be larger than the weight? Yes. For example, if we have an object which is naturally floating in this condition, and then we press it a little further into the liquid, and if we press it and release it, immediately it tends to bob upwards. Why that happens? Because the moment we pressed it further in, we have broken this equilibrium condition. So the buoyant force will exceed the weight in that case. Okay. So it will tend to accelerate upwards, right? So a wooden block or something which is floating in liquid, if you press it in, it tends to come up on its own again. In fact, later we'll study, not only it tends to come up, it will tend to oscillate if you press it and release it. It will continuously oscillate. So that initial upward motion, part of the oscillation, that will happen because the buoyant force has become greater than the weight. Okay, so a good example of this is the case of a floating iceberg. Okay. Consider a solid iceberg. So when we consider an iceberg, the density of ice we know is 0.9 gram per cc, floating in pure water, not sea water. So we are taking a different situation. Sea water is basically salt solution, it's saline, so it has a different density. But here we'll consider pure water, so it's 1 gram per cc. Okay. So as it floats, the portion of volume submerged with respect to the total volume is actually 0.9. So 90% of the floating iceberg is actually submerged underwater, and what you see above is only 10% of its volume. Okay, so hope this example was clear. Now let's see a somewhat different type of example where buoyancy is coming into place. Okay. So now we have this situation like we have, let's say, a wooden block like this, okay, which is floating in water, solid wooden block. But we have also placed a heavy object on it, like a metallic object, okay, in order to press it down. So it's now, you can see it's just about floating. If the object had been even slightly heavier, it would have made it sunk. Let's assume it is this case. So it's just about managing to float. So we have a wooden block. Okay. So the density of wood is a solid wooden block. So the density of wood is given to us as 0.5 gram per cc, and it has dimensions okay, so this is the length and this is the side width, and also the depth is the same, so it's L into B, where L is equal to, let's say, 20 centimeters and B is 10 centimeters. Now this is a metallic object, okay, and of course it's floating in water which has density 1 gram per cc. So the wooden block loaded with the metallic object on top is just about floating. Just about floats. It's in a limiting kind of condition. You put even a microgram of mass on top of it, it will sink. Okay, so it just about floats. So we have to find the mass of the metal object. How much is the mass of the metallic object? Just try this out now. So the wooden block is actually, I mean, three-dimensionally speaking, it's like a cuboid, which has dimension like this. So you can see it's a solid wooden block whose density is half the density of water. So if we had not placed this metallic object on top, it would have floated comfortably with only half the volume submerged, because the relative density is 0.5 with respect to water. Okay, but the presence of the metallic object, it's pressing it from above and causing it to just about float in a limiting condition. So what is the mass of the object in that case? Yeah, Jagannath, what I had told you about that equation, that is only the case of this particular example. So as we solve it, I'll explain it. So the general condition for floating is that the weight is balanced by buoyant force. But only when the object which is floating is made of uniform density, then we can write the weight of the object is equal to uniform density into volume into g. Okay, so let's verify your answer, Parth. So there are two ways we can do this. One is we can make the free body diagram exclusively for the wooden block. That's also a decent method to go about this. So the wooden block will be pressed with some normal reaction from above, which the metallic object will be applying on it. It will have its own weight, of course, which will be density of wood into the volume of the block into G. And of course, there will be buoyant force. Now the buoyant force will be equal to density of water into the total volume of the block only, because it's completely submerged into G, because it's fully submerged. Okay, and this normal reaction will be equal to the weight of the metallic object. This is one way of doing the question, that we understand that that metallic object, it is experiencing normal reaction. So let's write this as M prime, whereas M is the mass of the wood. This is so quite easy now. You can see that the buoyant force is balancing the sum of this plus the weight of the wooden block. So that is balancing the total weight. Okay. So density of water into this is equal to M prime G plus density of wood into this. So M prime, the mass of that metallic object, you can see, is the difference of their densities into the volume. So 1 minus 0.5 in gram per cc into 20 into 10 into 10 in cc. So the mass of the metallic object must have been 1 kilogram. So if we make it even slightly more than 1 kg, it will tend to make it sink. It will tend to make the block sink. Whereas if we make it less than 1 kg, the block will come up a little in the water, because it will not require that much buoyant force. So the submergence will be less than its total volume. Okay. So hope all of you understood the concept of application of buoyant force for a floating object, and in general application of Archimedes principle to calculate buoyant force through these examples. So actually this is all there is to fluid mechanics. I mean to hydrostatics. Next time we'll be also looking at fluid dynamics or hydrodynamics, which is the physics of a fluid in motion. But yes, there are lots of varieties of questions to solve within this concept set only. So we will look at more of that in the upcoming lecture. Also make sure to review your physics major test that happened on Sunday. So you can discuss your doubts and questions from that also in the upcoming lecture. So that's it for today, people. Wish you all the best.
Thank you, sir. Bye, sir.
Thank
Okay, bye, people.
Thank you, sir.
Okay, people.
Yes, sir. Bye, sir.
Bye. Bye.
Thank you, sir.